Time for us to do some problems involving the gradient, which also means we're going to do some problems involving directional derivatives. Answering the question, how fast are we changing if we go that way? As always, it's important that we do practice. The more practice that we do, the better we become, and we want to become great and fantastic at this. So make sure you do as many problems as you can. If you're following along with the video, make use of the pause button. See a problem? Try it yourself first and see how far you can get. And if you ever need any help, I'm here. You just need to unpause me, and we'll have a great time together. Well, let's begin. Our first problem. Well, let's just start by practicing the gradient of f. And the way we remember this is saying, hey, gradient of f really just says collect our partial derivatives. And as long as we remember that, it's actually not so bad. In fact, this will be kind of a fun problem. So what do? Well, the gradient of f will be the vector. So gradients are vectors. So our answer should be a vector. And it's a vector which consists of partial derivatives. Partial f, partial x, partial f, partial y. Now the variables x and y correspond to the variables x and y. So we just are taking our partial derivatives and putting them together. Well, so we take the derivative first with respect to x. All right, derivative of sine is cosine. And inside stays the same, times the derivative of the inside with respect to x. Well, y. Derivative of minus x cubed with respect to x, minus 3x squared. Derivative of x times y with respect to x is y. That's the first entry. Second entry, similar thing, but now take the derivative with respect to y. Derivative of sine of xy with respect to y, well, chain rule. So derivative of sine is cosine, inside stays the same, times by the derivative with respect to y of x times y, and that's x. Derivative of x cubed with respect to y is 0. There is no y. And the derivative of xy with respect to y is x. And we're done. Aha! Cool! Wow, we should do more problems with the gradient. Well, really right now we're just practicing doing the gradient. And of course there's always the let's do something with it. And that'll come up in future problems as we go along. All right, well, good. Nice warm-up problem. So let's keep going. Our next problem. Find the gradient of g for the function g of x, y, z is x squared times z plus natural log of 1 plus z squared. Okay, so this is a function of 3 variables. How do we know? Well, because look, there's x, y, and z. Now you might say, whoa, hold on. You said there are 3 variables. I only see 2 showing up on the output. The number of variables that we say our function depends on is how many inputs there are. So since there are 3 inputs, it's a 3 variable function. It just happens that one of the inputs is not used in producing the output. But we still have to pay attention to it. So what's our gradient? Well, our gradient in this case, it's still a vector because gradients are vectors. And it's a set of partial derivatives. So we do it with respect to each variable. So we can write it as g sub x, comma, g sub y, comma, and g sub z. There we go. So, again, just go through, take derivatives. Derivative with respect to x. Well, derivative of x squared z with respect to x will be 2x times z, and the other term, log of 1 plus z squared, no x. Derivative with respect to y, and we do have to take it, remember, every single input, and y is an input. So, derivative with respect to y, 0. Come to our last entry. Derivative with respect to z. Well, there's an x squared times z, derivative of that, x squared, plus derivative of natural log of 1 plus z squared. So the way we take derivative of natural log is we put the inside part, 1 plus z squared, into the denominator, 1 plus z squared. Now take the derivative of the inside you put that in the numerator. And that's how the chain rule works. Derivative of natural log is 1 over. So chain rule says, okay, take the derivative of the outside, plug the inside in. So that's how you get 1 over the inside times the derivative of the inside, and that's why you have the derivative on the top. And so derivative of 1 plus z squared with respect to z is 2z. Make those a little bit bigger, and we're done. Because it said, find the gradient. And we found it. It's right there. I think maybe the most tricky part about this problem is to remember, hey, you do need to have something in that slot. So however many variables you have as your inputs, that's how many slots you need in your gradient function. Always remember that. Okay, good. Well, now that we've had some good warm-ups, let's see what the next problem will have. So, find all the points so that our gradient is 0. Now you'll notice it's not just a normal looking 0, it's kind of a bold 0. What that means, it's really representing the 0 vector. Okay, so if we want to say our gradient is 0, what that means is we're looking for all the entries are 0. So if you want to say two vectors are equal, all the entries have to be equal. So let's take our gradient. Okay, so our gradient of f, we'll just write it down. Take the derivative with respect to x, 2x minus 6 plus 2y, comma, derivative with respect to y, 4y minus 10 plus 2x. And notice, of course, the 42 goes away and all the things, and we're just partial derivatives, so forth and so on. So we want this equal to 0, 0. So what we have is we're saying, aha, this first entry has to be 0, and our second entry has to be 0. So what we've done is we've kind of have compressed by saying, oh, the gradient is equal to 0, really is saying, oh, each partial derivative is equal to 0. So now we have really two equations, and let's write them down. And so the first equation, 2x minus 6 plus 2y equals 0, well, we can write that as 2x plus 2y equals 6. And here, 4y minus 10 plus 2x equals 0, we can write that as 2x plus 4y equals 10. Well, before we do too much, let's just say, look, everything is even. So let's divide by 2. X plus y equals 3. X plus 2y equals 5. Okay, now our bread and butter. Two equations, two unknowns. We do this all the time. And there's lots of ways to do it. I really like combinations. In other words, multiply one of these equations by a number, combine it with the other, and hopefully if we do it well, nice things will happen. Especially, if we're good, if we've lived a good, clean algebra life. In this case, it looks like it's set up so that nice things will happen, almost as if the person who wrote this problem wanted us to succeed, because they wanted us to succeed. So, as an example, I can multiply the first equation by a minus, and I can combine together. You'll notice what happens. The x's will cancel. Ah, nice. And you have a minus y plus 2y. Well, that's y. Then you have a minus 3 plus 5, which is 2. So we get, aha, y equals 2. Well, now you know that y equals 2. What do? Well, you can substitute. That says x plus 2 equals 3, so we get x equals 1. And therefore, there's only one solution. And so we get the single point 1, 2. Now in this case, it was because we got down to the situation where we had two equations and two unknowns. Now you would always get down to that situation. That's not a surprise. But they were nice equations and nice unknowns. They could have been much more interesting. could have had polynomials, could have had other exotic functions, in which case you'd have to do a bit more work. Now, we are going to be interested in knowing when the gradient equals 0. Think about what the gradient represents. The gradient is our analog of the derivative. And we said, ooh, the derivative equals 0 is really important. In fact, we said that it was critical in our understanding of the function. So we want to get to the point where we're comfortable in saying, okay, find where the gradient equals 0. Geometrically, it's saying find where the tangent plane equals 0, and that, of course, will be an interesting point. So we're going to get lots of practice doing this in future sessions. So a shadow of things to come. All right, good. Well, let's keep going. All right, our next problem. So, suppose you have the function g of x, y, z, and it's written there. Find the rate of change of g at the point 1, 1, 1 in the direction of the point 3, 0, minus 1. Okay, so we have a function, and there's, of course, this really important phrase, rate of change. Now, rate of change is just a very fancy way of saying derivative. So, all right, we know how to make that substitution. We see the word rate of change, we're like, okay, this is a derivative problem. And not only is it a derivative problem, there's another word that jumps out to us. And you can see it. It's this word, direction. So it's like, oh, we're looking for a derivative in a particular direction. So we want a directional derivative. So that's what we're going to do. We're going to find a directional derivative. Okay, good. So now we know what our problem is. The next thing to do is say, well, how do we go about doing directional derivatives? Well, our problem involves a function which is nice. It's polynomial. Polynomials are nice functions. Now, usually when we say nice in calculus, we mean, hey, we can take derivatives. And that's what we mean here. We can take derivatives. So we say, okay, so if we're looking for our directional derivative of our function at some point p, that is, according to our basic setup, the gradient of our function at that point dot with u. So there's a couple things we have to make sure we know. Which point are we at? What's the gradient at that point? What's our unit vector? So we have to go through and figure those things out. Now we know which point we're at, but let's be careful because there are actually 2 points listed here. So we want to make sure we know which one we care about. Which one is our point? Well, it says at the point 1, 1, 1. So that tells us what P should be. The point P is the point 1, 1, 1. So what about the second point? Well, it says the direction of the point 3, 0, minus 1. So that's telling us something about our direction. In other words, it's giving us information about u. Now, is that u? The answer is no. It can't be u. I mean, the easiest reason it can't be u is u stands for unit vector. And this is definitely not a vector. It's a point. So, what is it? Well, it's information that helps us find u. So the idea here is we're somewhere in three-dimensional space. Well, not just somewhere. We know exactly where. We're at this point 1, 1, 1. Let's say it's over here. And we're going to the point 3, 0, minus 1. I don't know exactly where that is. Let's say it's over here. That's not accurate, but it's not about the accuracy. We just need to build up our intuition. So the question is, what's that direction? That's the direction we need to be going. So we need to figure this out. All right, well, let's start by finding a vector that goes from 1, 1, 1 to 3, 0, minus 1. We know where we start, we know where we stop. So a vector that does that is we look at the changes. So we say, okay, we went from 1 to 3, so we went up by 2, 1 to 0, down by 1, 1 to minus 1, down by 2. So that's a vector. Is it our unit vector? Well, no, it's not a unit vector. It's way too big. So the next thing to do is say, okay, let's make it a unit vector. No problem. What we do is we're going to take 1 over the magnitude, 2 minus 1 minus 2, times 2 minus 1 minus 2. Oops, that doesn't need to be there. That's how you turn a vector into a unit vector. You scale out by its magnitude. Now in our case, well, this would be, the magnitude would be the square root of 2 squared is 4, negative 1 squared is positive 1, because you're squaring. Negative 2 squared is positive 4. 4 plus 1 plus 4, that's nice. That's the square root of 9, which means your denominator is 3. So we can come to the conclusion, lo and behold, that our vector u is 1/3 2 minus 1 minus 2. Now, if you wanted to, you could distribute the 1/3 in. I think that there's reasons not to. Whichever way you prefer, that's okay. They both work. They both work. I'll point out why maybe it's not the best thing to distribute it in. Well, I'll just tell you right now, I don't like fractions. That's really what it boils down to. Fractions are tough, and I try to minimize the number of fractions. So by pulling that 1/3 out to the front, there's only going to be 1 fraction instead of 3. Aha, that's good. I cut my number of fractions down by quite a lot. Now, we've handled the u. Let's turn to the gradient. So we'll say our gradient, now in this case I wrote f, it should have been g, but that's all right. We'll write it here. Gradient of g is our gx, gy, and gz. Well, might run out of space, but we'll do our best. Take the derivative with respect to x, so we only look for terms with x, and there's one x term there. So the derivative of that with respect to x would be z, and nothing else looks like it has an x. Okay. Derivative with respect to y, there's no y. That'll be 10y, and that's not a y. Aha, derivative with respect to y of that will be plus z, and that's it. Comma. Now look for things with x. Take derivative with respect to x. So that'll, look for things with z. Or take derivative with respect to z. So that'll be an x. Not comma. Whoops. I wrote too many commas. Got comma on the mind. Okay. Minus 6. So x minus 6 plus y. And that's the gradient. Now, we need the gradient at our point. So, the gradient of g at the point 1, 1, 1 is, well, 1, 10 plus 1, 11, 1 minus 6 plus 1, minus 6 plus, not minus 6, it's 1 minus 6 plus 1, so that's minus 4. There we go. There we go. We can do arithmetic. Well, if not, do it twice, right? Okay, so put it together. We now have our gradient part. We have our vector u. So we can say, look, our answer will be what happens when we take our gradient, 1, 11, and minus 4, dot it with our vector, which is 1/3, 2 minus 1 minus 2. So the 1/3 you can just pull out in front, and now just do the dot product. 1 times 2, 2. Minus 1 times 11, minus 11. Minus 4 times minus 2 is plus 8. Okay, well, so what do we end up with? 2 plus 8 is 10, minus 11, minus 1. Then there's a 1/3, so minus 1/3. That's our answer, minus 1/3. Now you might say, well, what does that mean? minus a third. Well, what it means is, if you think about the rate of change, it's saying as we move in that particular direction, the amount we're changing in our output is scaled by negative 1/3 times the amount that we're changing in our input. Of course, that's only as we're close by. But in calculus, we really care about what's happening close by. What happens as we zoom very, very close? That's the idea. That's the idea. It's a lovely idea. All right. Well, good. Good. I think we can do another one. I think we have time for one more, right? One more problem. No problem. So here we go. Let f of x of y be a differentiable function. So we know we can take derivatives. Wonderful. Given that at 1, 1, the directional derivative towards the point 4, 5 is 8, and that the directional derivative towards the point minus 3, 4 is 1, find fx 1, 1 and fy at 1, 1. Okay, so one way to think about this is saying, hey, I know the rate of change in that direction, I know the rate of change in that direction. Can you tell me how I'm changing with respect to x, how I'm changing with respect to y? That's the question. And it seems reasonable, because let's think about what's going on here. So we have information, we know our function is differentiable, and we would say, well, let's think about our picture. We have some points. Let's actually quickly sketch our points. All right, so we have our point 1, 1. Okay, so here's our point 1, 1. And then we have some other points. We have the point 4, 5. And that'll be somewhere up here. And then we have the point minus 3, 4. All right, well, where will that be? Well, that'll be somewhere over here. Minus 3, 4. And we know something about our rate of changes in these directions. Okay, so we can say if we start from the point 1, 1, we know what's happening when we go in these two different directions. All right, how do we actually find our directional derivatives? Well, because it's a differentiable function, we have a nice tool. So what we can use is the following. Say, look, the way we find our directional derivatives is we would take our gradient at our point 1, 1, because we're coming from 1, 1. So that would be fx at 1, 1, comma fy at 1, 1, and we would dot it with u. That's how we could find our directional derivative. So we're like, aha, cool. Now, just for convenience, as we're working through the problem, let's go ahead and simplify this. We'll call these a and b as we move forward. These are what we're trying to solve for. Try to find a and b. So let's think about what our vectors u are, and we'll just make a note to recall ourselves. These are directional derivatives in the direction u. Okay, so that's what we find. Okay, so from the point 1, 1 to the point 4, 5. Well, that says we went up by 3 and up by 4. So that's the vector 3, 4. If we go from 1, 1 to minus 3, 4, well, we went down by 4, up by 3. Okay, good. Now, are these our unit vectors? And why not? Right, they're not. Well, the problem is they're not a unit. They're not length 1. So that's an easy fix. We can make them length 1. And we can actually do these in our head because there's not too many numbers involved, and the numbers that are pretty nice. If we take the magnitude, you take 3 squared plus 4 squared, 9 plus 16, which is 25, take the square root. This has length 5, and this one also has length 5. So, if I want to make these unit vectors, scale by 1/5 in front. Now I have unit vectors. So what we can say is our information says if we take our gradient, which we're writing as AB, remember AB, dot, well, let's go from 1, 1 to 4, 5. So that would be 1/5 times the vector 3, 4 is 8. Okay, so that equals 8, right? Because we have the directional derivative towards the point 4, 5. Directional derivative towards the point 4, 5 is equals 8. In a similar way, the directional derivative towards the point minus 3, 4, so that's taking our gradient dot, 1/5 minus 4, 3 is equal, that's the is, 1. Okay, so I'm going to do two things. Well, that is multiply by 5 just to get rid of my fractions. I like getting rid of fractions. And then I'll do the dot product. So 3 times A plus 4 times B has to equal 40. And minus 4 times A plus 3 times B has to equal 5. Good. 2 equations, 2 unknowns. The right number. So how do we go from here? Well, the way I like to do things is look for combinations that can get cancellations. So suppose we wanted to cancel off the A's. Well, I see a 3A and a minus 4A. So what I could do is I can multiply the first equation by 4, multiply the second equation by 3. And let's just see what happens. Now, these aren't random numbers, 4 and 3. It's so that when we look at what happens in the front, we get things such as 12A and minus 12A. In other words, just the right thing to get cancellation, which is great. Here we'll get 16B and 9B. So 25 times B equals 160 plus 15. Well, if you add 160 plus 15, you get 175. Okay, well, that's actually kind of nice. Does 25 divide into 175? It actually does. So if you do the division, we come to the conclusion B equals 7. Now that you know B, you're basically done. Because we can take that and plug it in. So for example, 3A, 4 times B is 28 equals 40, or 3A equals 12. So that says, aha, A equals 4. So you said A equals 4 and B equals 7. We have our solution. You can even check it. Works for this one, right? Because what do you see? You'll see minus 16 plus 21 does in fact equal 5. So remember, A and B were just shortcut names. So what we have is, hey, this f sub x at 1, 1, which is what we're trying to find, that's equal to A, and that is 4. And this f sub y 1, 1, that's B, and that equals 7. And we're done. So in some sense, it says, hey, if I know the directional derivative in a couple of directions, I can find information, which makes sense because really, if I know what's happening in 2 ways, that helps me figure which way is my plane tilted, because you have more or less 2 degrees of freedom, and so knowing 2 directions tells you how your plane tilts, and that gives away all the information you might want to know. Well, that was good. Lots of fun. Thanks for coming, and keep up the practice, because the more you do, the better you're going to get. So I hope to see you again soon. Bye.